All right, all right, all right. Hey, everybody. So, this is going to be our next lecture that we're going over. We just completed learning about slopes, learning about the slants of the line, remember? Right? And we plotted 2 points to make a line, right? So, this is how that previous information ties into statistics, right? So, our next lesson is going to be on scatter diagrams and linear correlation. So, studies of correlation and regression of two variables usually begin with a graph of paired data values x and y, right? Remember how we had those points that we plotted on the graph? All right. We call such a, a graph a scatter diagram. So, scatter diagram is a graph in which data pairs, x and y pairs, right, are plotted as individual points on the graph with a horizontal axis x and a vertical axis y. We call x the explanatory variable and y the response variable. Okay? So by looking at a scatter diagram of data pairs, you can observe whether there seems to be a linear relationship between x and y values. So for example, phosphorus is a chemical used in many households and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water where it can kill fish, plants, and other wetland creatures. All right. And this is where you can find information about that. Phosphorus reduction programs are required by law and are monitored by the Environmental Protection Agency. Okay. A random sample of 8 sites in a California wetland study gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable, right, that represents phosphorus concentrations in 100 milligrams per liter at the inlet of a passive biotreatment facility, and Y is a random variable that represents the total phosphorus concentration in 100 milligrams per liter at the outlet of a passive bio treatment facility. So here's the idea of what's happening, right? Let me just make sure I get it right. Okay. So please bear with me. I'm not a good artist. I'm just trying over here, right? Let's say that there's a that's supposed to be steam right there, right? Let's say that there's a factory, right? A biotreatment factory, and then there's some type of trying to imagine how I'm going to do this. Some type of like inlet, right? So the water is going in, right? All right. So the water is going like into the biotreatment facility, right? And then it's coming out, right? And then it's coming right back out of the facility. I don't know, something like that, I guess. Maybe the water comes in here and then comes out there, something like that. But the point is, right? The water is coming into the treatment facility. It's being treated, drained of the phosphorus, and then we want to see how much quote unquote clean water comes out, right? So it sounds like this is not 100% of a cleaning, right? Like they can't pull all of the phosphorus out the water, but hopefully they could pull out enough that it doesn't kill, wildlife and plants, etc., etc., etc. Okay, just so that we have the idea. So here you go, right? These are your numbers, right? You have 5.2, 3.3, 7.3, 5.9, 6.7, 4.8, etc., etc., etc. Right? Remember that these are pairs, right? X and Y are pairs. These numbers go together, right? In their own unique column. All right? Boom. Anyway, here's what we have to do. Step one. We want to make a scatter diagram for these data points right here, right? All of these individually, these data points. Okay. So remember when we spoke about the different quadrants, right? We had quadrant one, two, three, four. When you're doing a scatter diagram, you'd be happy to know you only need to work with quadrant one. Oh boy, can't draw. Told you guys that I'm not an artist, not an artist. All right. So this will be your horizontal axis, X, your vertical axis, Y. There you go. I'm trying over here. I'm trying. Okay. So, okay, step one, draw the axis, right? You draw the diagram. Let's say that. The next thing that you want to do, all right, because you're in control, right? You're the one that's gonna determine how your axis is gonna get broken down, right? But how do we determine what numbers we should use on the axis, right? Like should I go by ones? Should I go like this is zero and then go one, two, three, you know? Or would it be smarter? Would it be smarter for me to go by twos, you know? Maybe I should go 0, 2, 4, and then maybe 6. Or maybe I should go by threes, right? So say 3, 6, 9, right? It's up to you how you're gonna decide to label your axis, right? You choose your starting point, you choose your step up, right? Like how you want to go. Like, do you want to increase it by twos, by ones, by threes, right? You're in control of that. So, but there's something that we need to pay attention to, right? So I'm just gonna look at the x's right now because I'm dealing with the x-axis. I'm looking at all the numbers, right? All the numbers that I have right here. So I have 5.2, 7.3, blah blah blah. So this is what I'm looking for. I want to know what's the largest number, right? In that set right there. What's the largest number? The largest number here turns out to be 8.3, right? So what does that mean? That means that whatever axis I decide to go with, right? I have to make sure that 8.3 is included in the conversation, right? Because that's the largest number. And that's it. So I think I'm gonna go up by twos, right? I don't have to, but I'm gonna go up by twos, right? So I'm gonna say 0 to 2, 4, 6, 8. Now remember that's 8.3, right? So I can't just stop at 8. 8 is not including it's not including 8.3. So I have to go one more. I'm gonna go to 10. All right. Now we're gonna do the same exact thing for Y. Same exact thing for Y. So let me just erase this real quick. All right, let me look at all the numbers at 3.3, 5.9, 4.8. All right, so it looks like 7.1 is gonna be my highest, right? So whatever I do, I have to make sure that I include a bound, right? That's gonna include that 7.1. Okay. All right. So I think I'm gonna Mm, just thinking about it. I think I'll just go up by twos, just the same way. You do not have to increase the X and the Y at the same rate. It's up to you. You're in control. I just feel like going up by two. So 2, 4, 6, and that's about it at 8. All right. And that's good. That's good enough. Okay. Now let me change up my color a little bit. I got some options here. I'm gonna go with the pink. Should I go with that? Let me think. Let me think. Let me think. All right, you know what? I'm gonna go with the blue. I'm gonna go with the blue. Nah, nah. Let me go with the pink. Let me go with the pink. Let me go with the pink. All right. sometimes it's real hard to choose a color, you know? Sometimes you got to really think about it. Okay. And this is just random, by the way. I'm just trying to have a little fun. All right. You can do this all in one color if you want. I just want to make it pop for you guys a little bit. Anyway, right? Remember what I was saying before, right? These numbers go together, right? They go together. So I want to plot each one of these, right, on our diagram right here, right? So first point is going to be 5.2 and 3.3. So just to recap real quick, how do we do this? You're going to come across the x-axis to where you believe 5.2 will be. I think it'll be somewhere like around here. And then the other number was 3.3. I believe 3.3 would be somewhere around like here, right? And you kind of just go to where you think they would intersect that, and then you just make a dot, right? Now, me personally, not really a dot fan. I like to do X's, so that's actually how I'm going to do this. So I'm actually going to make this an X. All right. Now, again, this is your preference. You want to use a dot, you want to use an X, your choice. All right. But this is how you match it up, right? You go on the X axis first, right? Then you go up the Y axis and you just make a mark where you believe they will intersect that. For the rest of the points, I'm not going to do this, but I just want to show you how to at least do it with the 1 point, right? Also, I'm going to erase these lines here because this is not what I want this to look like. All right. So that's 1 point. Okay. Next point, 7.3, 5.9. All right. So I'm going to come across to where I believe 7 would be, 7.3, and then 5.9. I'm going to go up to where I believe 5.9 would be. So somewhere like right here. All right. And then 6.7, 4.8. I'm going to go across to where I believe 6.7 would be. 4.8, I believe, would be like right here. All right. Next, I got 5.9, 4.5. So 5.9, 4.5. I feel like it's right here somewhere. All right. All right. Remember also, right? The name of this is what? Scatter diagram, right? Scatter diagram. So they shouldn't be on top of each other, the marks that we're making, right? They shouldn't be in like necessarily like a perfect straight line. They should be scattered, right? For lack of a better term, scattered, right? Okay. 6.1, 4.0. That I feel like that's like right there, give or take, right? And again, we're just estimating, so you just do the best you can, right? Just do the best you can. 8.3 to 7.1. All right, 8.3 all the way over here. 7.1, I think, is somewhere up here, right? I'm just circling these as a way to mark off that I've already done that point, you know? Anyway, next one, 5.5 to 3.6. 5.5 to 3.6. I don't know. Really close. Let's say like right there. All right. And then 7.0, 6.1. So 7.0 to 6.1, something like that. Right? See how they're randomly scattered over here? Right? That's what I want. Some random thing. You don't have to make your first point so big. You know, like I was kind of doing that for did not expect all of that to get erased. But I was just kind of doing that for to show you guys where that came from. And some of my points got erased, so let me just verify them again real quick before I continue. 5.2. Oh wait, I can forgot about that. I can just do one of these, right? I can just undo it. That's not gonna work for me. Let me see. Let's see if we can get that. Okay, that got erased. All right. All right. So there's two more points. 5.5, 3.6, 5.5, 3, 3.6. Say somewhere like right there. And then 7.0, 6.1. Whoops, I didn't mean to go down so deep. 1 second. 7.0, 6.1, somewhere like up here, right? And let's just make sure I have them all right. So I have 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. How many points I have it? 1, 2, 3, 4, 5, 6, 7, 8. Okay, okay. I have one extra point somewhere. All right, let me just. I'm like nervous to erase it. I don't want it to erase all of it. Oh, there it goes. And erase everything. Let me just get that back. All right, we're gonna you know what I'll do? How about this? All right. I'll just scratch out one of the points. All right. Let's just do it like that, just to save time. All right. But you have 8 points. You should have 8 dots or X's, like how I like to use it. All right. Boom. All right. In a nutshell, that's the scatter diagram. Something else that I want you guys to do as well, I want you to label, right, your scatter diagram. So right here, let's recap. X is a random variable that represents the phosphorus concentration in 100 milligrams per liter at the inlet, right? So that being said, right, let me scroll down. This is the inlet in 100 milligrams per liter, right? So that means that going back to our story, all right, I'm trying to write sideways now, so bear with me. This is the outlet, right? In 100 milligrams per liter. Yeah, I'm trying my best at that one right there. All right. But the point is, right, you want to have your graph labeled, right? You want to label the x-axis, label the y-axis, right? The next thing that I want you to do, this is why I was kind of debating my colors a little bit earlier, right? I want you guys to draw a line of best fit, right? Draw a line like so that goes through your points, all right? The line doesn't have, I don't want the line to actually touch the points. I don't want you to connect the points. I want you to draw a line that passes through the points, all right? This is what's known as our line of best fit, all right? More to come about that. But this overall, this is how you design, how you draw a scatter diagram, right? This is what I'm going to be asking you guys to do, right? On your next exam, you draw the scatter diagram. So what do? You first draw your diagram, your X and your Y axis, right? You're going to determine your how you're going to put your numbers out, how you're gonna spread your numbers out, right? Do you want to go up by ones? Do you want to start at one? All of that you're in control over. But remember, what's most important, you want to include the largest value from your data set when you're considering making your access points. All right. And then of course, please don't forget the labels. Give me those labels, right? They're gonna be posted in the story, right? That's the X. And you know what? I forgot to highlight the Y. Let me highlight where the Y is. Y is a random variable that represents the total phosphorus concentration, 100 milligrams per liter at the outlet. All right. Okay. All right. I'll leave that up in case anybody wants to pause and copy, etc., etc. All right. Now, while I do try my best to draw in front of you guys, I do want to acknowledge that I am not an artist. All right. So because of that, I want to give you guys like a computer drawing that just looks a lot better than what I attempted to do. All right. But I'd love to talk to you guys about it real quick. All right. So as we said before, here's our x-axis. This is our outlet. All right. I want to talk about this part in the graph real quick. Um, Good. So I want to talk about this part in the graph real quick, right? So let's say that I have a graph and then I make this mark right here, right? Imagine what I'm doing is that I'm squeezing the axis together, right? So we all know that right here is going to be zero, right? But let's say I don't want to start at the number one, right? Like say I'm not even interested in 0 and 1. I just want to start at where 5 is, for example, like what they did, right? So I'm squeezing the axis together, right? I'm skipping over 0, 1, 2, 3, 4, and I'm just going straight to where 5 is, right? That's what that little line means. That means that I'm squeezing my axis together, right? Same thing on the other side as well, right? You can do one of these on the other side, right? And it means the same thing, right? I'm trying to squeeze the y-axis together, right? I don't want to start at 0 or 1, right? I want to start at where I want to start. I want to start at 3 and then work my way up from there, right? No problem, right? That's the way the computer wanted to do it. Right? Just wanted to explain that little part right there. And also on your test, if you want to do the same thing too, no problem. No problem. All right. So again, we have our labels, right? This is our inlet. This is the outlet over here, right? And then they decided to go up by ones. They started at a different point. You have all your dots, as you can see, and we have our line of best fit that goes straight through. Okay. All right. Next thing I want to talk about is the interpretation of this, right? So we plotted the points, yippee, right? But what does that mean? Like what information are we getting from doing this? All right. Which is also going to be a question on your exam as well, right? It's not just plot the graph. What is it telling you? Right? So here's our interpretation, right? So you want to comment on the relationship between the X and the Y graph as shown, right? So by inspecting the figure, we see that smaller values of X are associated with smaller values of Y. And larger values, let me do one of these, right? All right. Smaller values of X are associated with smaller values of Y. And larger values of X is associated with larger values of Y. Right? There we go. Roughly speaking, the general trend, that's what I care about. The general trend seems to be reasonably well presented by an upward sloping line, as shown in the diagram, right? So, one of the questions I'm going to ask you after you draw all of this, what would you estimate the slope to be, right? Like just what do you think this slope would be? right? Is it a positive slope, right? That's increasing from left to right, same way that we read a book, right? Positive slope. Or is it a negative slope that's decreasing from left to right, same way that we read a book? That's a question I'm going to ask you, right? What would you estimate your line of best fit to be, your correlation, right? What would you estimate it to be? Is it positive, right? Or is it negative? Very simple question, very simple answer, right? Obviously, for this one, this is a positive correlation. Okay, good to go. All right, let's elaborate on this idea just a little bit more. Right. So, of course, it is possible to draw many curves close to the points in the figure, right? But a straight line is the simplest and most widely used in elementary studies of paired data. We can draw many lines in the figure, but in some sense, the quote unquote best line should be the one that comes closest to each of the points of the scatter diagram. To single out one line as the best fitting line, we must find a mathematical criterion for this line and a formula representing the line. And this is going to be done in the next section. That was the method of least squares. So another problem precedes that of finding the best fitting line, right? That is the problem of determining how well the points of the scatter diagram are suited for fitting any line. Certainly, if the points are a very poor fit to any line, there is little use in trying to find the best line, right? If the points of the scatter diagram are located so that no line is realistically a quote unquote good fit, we then say that the points possesses no linear correlation. And then we'll see some examples of scatter diagrams, right, for which there is no linear correlation. Now, listen, I'm gonna tell you guys this, right? At least in this class, all right, there's no such thing as no correlation. There's no such thing as no linear correlation. All right. There's always a correlation, right? It's either positive or it's negative. So when you're taking your test and they give you that multiple choice like answer positive, negative, or no correlation, do not choose no correlation. All right. It's one of the other two. It's either positive or negative depending on the data and the way that the graph looks. Okay. But let's look at some examples of no linear correlation, right? So let's say I have my data, right? And when I do my graph, it comes out looking like this. That's not linear, right? It's hard for me to tell, is it positive, is it negative? It looks like both, right? Oh boy, let's say that we have B now, right? Let's look at this graph. This is just a straight up scatter, you know, right? This is really hard to tell which one is like if it's positive or negative, you know, and like just by looking. That's what I'm trying to say. It's really hard to tell just by looking. All right. All right. So if the points seem close to a straight line, we say the linear correlation is moderate to high depending on how close the points lie to a line. If all the points do, in fact, lie on a line, then we have what's called a perfect linear correlation, right? And then this next figure I'm going to show you guys, we'll see some diagrams with perfect linear correlation. In statistical applications, perfect linear correlation almost never happens. All right. So let me show you guys what that's looking like. We're going to go step by step through these real quick. All right. I'm just taking a little bit slow, so just bear with me. I'm going to go step by step. All right. So here we go. Here we go. Here we go. So the variables, right, x and y, are said to have positive correlation if low values of x are associated with low values of y, and high values of x are associated with high values of y, right? So we're going to show you these two diagrams right here in which the variables are positively correlated. On the other hand, if low values of x are associated with high values of y, and high values of x are associated with low values of y, the variables are said to be negatively correlated. All right, let's take a look. Let's take a look. All right. So this is a scatter diagram with moderate and perfect linear correlation. So first thing first, we're looking at moderate linear correlation, right? So A and B, these are moderate linear correlation, right? We have scatter dots all over the place, and we have our line of best fit that goes straight through them, right? This is the positive. This is positive linear correlation. EAR correlation. And this one over here is the reverse. This is negative correlation. Right? So that's our moderate linear correlation. All right. Next, I'm going to show you the perfect linear correlation. You'll probably never see this in real life. This is a hypothetical textbook kind of example, but still fun to talk about, right? Still fun to talk about. So here we go, right? Perfect linear correlation, right? Every single dot is on the line. They're all on the line, right? They line up in a line, and the line goes perfectly right on top of each one of them. This is perfect linear correlation, right? This is the positive, this is the negative, right? Perfect linear correlation, right? If only the world was perfect, we'd see this all over the place. All right. So just want to talk about this just a little bit in general when we have a scatter diagram, right? What is a scatter diagram like telling us? What is it trying to tell us? All right. So a scatter diagram shows the relationship between two paired variables, x and y. For each pair, xy, of a data set, we plot the point on a grid with horizontal axis x and vertical axis y. To the extent the data points on the graph fall closer to a straight line, we can say that the relationship between x and y is more linear. To the extent that the data pairs are scattered over the graph, we say that there's no linear relationship between the x and y, right? And that is apparent. Okay. This is all good stuff. All right. Now, remember I told you that there really is no such thing as no correlation, right? There is a mathematical way to figure out what a correlation is, right? So let's talk about that, right? One way, of course, is just graph it, and then you could tell, oh yeah, that's a positive, oh yeah, that's a negative correlation, right? But here's how you can get a number to both display to you what the correlation is and how strong it is. Okay, so here we go right here. So we're going to talk about sample correlation coefficient R. So looking at a scatter diagram to see whether the line best describes a relationship between the values of the data pairs is useful. In fact, however, you're looking for a relationship between two variables, making a scatter diagram is a good first step. There is a mathematical measurement that describes the strength of a line association between two variables. Excuse me. This measure is the sample correlation coefficient R. The full name for R is the Pearson's product momentum correlation coefficient, named in honor of an English statistician called Pearson, right, who sadly passed away in 1936, who is credited with formulating R. All right. All right. So the sample correlation coefficient is a numerical measurement that assesses the strength of a linear relationship between two variables x and y. R is a unitless measurement between -1 and 1. In symbols, right? -1 is less than or equal to R, which is less than or equal to 1. If R is equal to 1, there is a perfect positive correlation. If R is equal to -1, there is a perfect negative linear correlation. And if R is equal to 0, there is no linear correlation. The closer R is to 1 or -1, the better a line describes the relationship between the two variables of x and y. Okay? Positive values of R imply that as x increases, y tends to increase. Negative values of R implies that as x increases, y tends to decrease. The value of R is the same regardless of which variable is the explanatory variable, right? And which is the response variable. In other words, the value of R is the same for pairs XY and the corresponding pairs YX, right? The value of R does not change when either variable is converted to different units. Okay, really, really interesting. Uh, all right, I just want to put a picture to what we've been describing earlier. Okay. So this is a positive linear correlation. And as you can see, high values of X, big values of X, are associated with high values of Y, these dots over here. And low values of X are associated with low values of Y over here. All right. Just want to show you guys the negative one before we continue. Oops. Okay. That's our positive. For our negative, it looks like this. All right. So negative linear correlation, right? Low values of X are associated with high values of Y, and high values of X are associated with low values of Y, right? That is our negative linear correlation. Right. And then last but not least, if we have some kind of truly scattered diagram, right? This is what we would call little or no linear correlation, right? We have them all over the place, right? Low values of X with low values of Y, high values of X with low values of Y, high values of X with high values of Y, low values of X with values of Y, right? But we can use our criterion, right, to figure out how much more negative or positive this correlation would be. Right? So now, I don't know if you might have guessed this by now, but there is, just like the standard deviation, we had the computation formula. There is a computation formula for R, right? The defining formula for R shows how the mean and standard deviation of each variable in the data pair enter into the formulation of R. However, the defining formula is technically difficult to work with because of all the subtractions and products. A computation formula for R uses the raw data values of X and Y directly, right? So we just want to make it simple for right now, all right? Just want to show you guys what that is. By the way, this computation formula is on your formula sheet. All right. So you don't have to commit this to memory. All right. And you guys have your formula sheet that you can use on your homework as well as on your test. All right. So please, you don't have to memorize this. It'll be there for you. All right. And there goes our formula right there. So how to compute the sample correlation coefficient R requirements. You want to obtain a random sample of n data pairs, right? X and Y. The data pairs should have a bivariate normal distribution. This means that for a fixed value of X, the Y value should have a normal distribution, or at least a mound-shaped and symmetric distribution. And for a fixed Y value, the X value should have their own appropriately normal distribution. So here we go. All right, procedure. Step one, using the data pairs, you want to compute the sum of X, the sum of Y, the sum of X squared, the sum of Y squared, and the sum of X times Y, right? With N equal to our sample size, right? And you have the sum of X, sum of Y, sum of X squared, sum of Y squared, and sum of X times Y, you are ready to compute the sample correlation coefficient R using the computation formula. This is it. And it reads R is equal to N times the sum of X times Y minus, in parentheses now, the sum of X times the sum of Y, all of that divided by the square root of N times the sum of X squared minus the sum of X squared times the square root of N times the sum of Y squared minus the sum of Y and N squared. Be careful. The notation sum of X squared means first square the x's and then calculate their sums. Whereas the sum of X squared means first add all the X values together, and then square the result, right? So notice, right? When it's the sum of X, you have the squares on the outside of the parentheses, right? That means add up all your X's first and then square the answer. But when you see the sum of x squared, right, that means that you want to square all your individual numbers first and then, right, add up the answer, the numbers that you get from that. Okay. Not too bad, not too bad. All right. So I do want to talk about an interpretation a little bit. So it can be shown mathematically that R is always a number between +1 and -1, i.e., -1 is less than or equal to R, which is less than or equal to +1. Right? This next table gives a quick summary of some basic facts about R. For most applications, we will use a calculator or computer software to compute R directly. If you're wondering, yes, your calculator can do this in its totality, right? However, to build some familiarity with the structure of the sample correlation coefficient, it is useful to do some calculations for yourself. Example 2 in the guide exercise will show you how to use a computation formula for R. So let's begin. All right. All right. So we're going to talk about computing R. We are going to need a story though. So bear with me 1 second. And I'm going to show you that table as promised. Okay. So here we go. Computing R. So sand driven by wind creates large, beautiful dunes at the Great Sand Dunes National Park in Colorado. Of course, the same natural forces also create large dunes in the Great Sahara and Arabia. Is there a linear correlation between wind velocity and sand drift rate, right? Let x be a random variable representing the wind velocity in 10 centimeters per second, and let y be a random variable representing the drift rate of sand in 100. Ooh, I can't remember what the GM is, right? Gigameter, kilometer, something like that, per centimeter per second. A test site at the Great Sand Dunes National Park gave the following information about X and Y, right? And you can look it up in the hydraulic, geologic, and biologic research at Grand Sand Dunes National Monument, proceeding in the National Park Service Research Symposium. Cool. Cool, cool, cool. All right. So let me show you that table. Then we go and jump into this. We're going to jump into our example. All right. This table is kind of just reiterating what we said before, but putting a picture to it, so it makes just a little bit more sense, hopefully. All right. So some facts about the correlation coefficient. If R is 0, there is no linear correlation among the points of the scatter diagram, and it will look something like this, right? We can't tell what it is, right? If R is 1 or -1, there is a perfect linear correlation between the X and Y values. All points lie on the least square line, right? So this is perfect, right? R equals -1, R equals +1, right? Now, let's say that R lies between 0 and +1. Then the X and Y values have a positive correlation. By this, we mean that large X values are associated with large Y values, and small X values are associated with small Y values. Excuse me. As we go from left to right, the least square line goes up, right? Between, let's say that R was between -1 and 0, right? That means that the X and Y values have a negative correlation. By this, we mean that large x values are associated with small y values, and small x values are associated with large y values, right? So as we go from left to right, the least square line goes down, okay? It's not a hard concept, but it does take a little getting used to. Mhm. So going back to our sand dune story, right? Just want to highlight a little bit, right? So x is a random variable representing the wind velocity, right? And y is a random variable representing the drift rate of sand in whatever unit GM per centimeter per second is, right? Anyway, let's look at our data. All right. Doing this. Oh, shoot. Didn't mean to do that. We're doing the same story. These are the numbers for the story. Right. We want to make a scatter diagram, and then we're going to say whether we expect R to be positive or negative. Very simple. Very simple. All right. So, first things first, get some space. Oh, you know what? Need a pen first, not a highlighter. Yeah. So that should be our real first step. Get a pen. Okay. And then there we go. Right? This is my X. This is my Y-axis. Right? And then remember that each one of these individually, these are pairs, right? Pairs, right? And I want to include, right? I want to include the largest value. So let me look at the X's. So largest number that I see here, 125. So I have to get to 125. I have to include 125 in my story. And here's another interesting little tidbit. I start at 70, right? Now, obviously, I'm not going to go from 1 to 125, right? So this is a scenario where I might want to skip a few numbers, right? I feel like I want to start off at 70, right? And then it's up to me how I want to increase it from there. I know that I want to get to 125, right? So I don't know. I feel like I'm just gonna go up by 10. My choice. I could have gone up by ones, I could have gone up by twos. I feel like I'm gonna go up by 10. So 70, 80, 90, 100, 110, 120. I still didn't get to 125 yet. 130. Okay. There goes my axis, right? Let me go back up to Y real quick. All right. I see my smallest number is 3, but my largest number is, looks like 62, right? So I know I want to include some type of bound that's going to have 3 all the way up to 62, right? So I'm thinking I want to go up to 62. Mm, yeah, I'm just going to go up by tens. I think that could do it. So I'm going to call this 10, 20, 30, 40, excuse me. Sorry about that. Let's call that 50. Let's call this 60. And let's call this final thing up here 70. All right. That works. Now let me switch this up a little bit. Get my pink. Make sure that it's working. All right. So my first point is 70 and 3, right? So what am I going to do? I'm going to come across on the x-axis to 70. Then I'm going to go up to where I think 3 is, right? I feel like 3 might be somewhere down here. All right. My next point is 115.45, right? So I'm going to go across to where I believe 115 would be, and then go up to where I think 45 would be, which I think is somewhere like right here. All right. My next point is 105.21, right? So 105, I think is somewhere over here, the 21, a little bit further there. Okay, that looks good. Next, after that, I have 82 and 7, right? So I'm going to go to 82-ish right here, 7-ish, like a little bit right here. All right. After that, I have 93.16, so I'm going to come across to like 93, and then I feel like 16 is somewhere like here, right? And then 125.62. So 125.62, somewhere like there. And then 88 and 12, right? So 88, whoops, 88 and 12, I think somewhere like right here. Boom, right? That's my scatter diagram, right? And I can imagine, one second. I can imagine a line of best fit just going through it that looks something like this. Again, I'm not an artist, just trying my best, right? Let's not forget our labels, shall we? Okay, so let me go back up to our story. So we said that X is wind velocity. So this is wind velocity. All right. And I'm just gonna put like a little X here to make no, so just so we know we're talking about X. And then my Y was what again? Drift rate of sand. I'm just gonna say drift rate, something like that. Right? Okay. So I drew my scatter diagram, right? Just looking, just looking at this diagram, right, for part B or whatever, right? Just looking at the diagram, what would we say that our correlation coefficient R would be? Like, what do we think it would be? Do we think it would be positive or it'd be negative? Right? Obviously, we know it would be positive, right? So we think that R is positive. And why do we think that, right? We think that because our line of best fit looks like an increasing line from left to right, the same way that we read a book. And also, more deeply, we can actually look at the individual points and we can see that low values of X are associated with low values of Y, and high values of X are associated with high values of Y. All right. So we would estimate R to be positive. Another question I could ask you is to interpret this for me, right? And what would the interpretation be for this, right? Use a story, right? So as X, which in our case is wind velocity, right, increases, Y, our drift rate, right? Increases. This would be our interpretation of what's going on in this scatter diagram, right? Now, just for conversation reasons, let's say that this was the opposite, right? Let's say that this was the opposite. Let's say that I have some diagram here and it has a negative correlation, right? So R is negative. The interpretation for this, for the negative, would be as X, whatever the X is in the story, right, increases, Y decreases, right? As X is increasing, Y is decreasing. That's if we have a negative correlation. Okay. Again, I'm not the best artist in the world. So just to make me feel good, I'm going to give you guys a digital drawing of what I attempted to draw here. Here we go. All right. So as the wind speed is increasing, the drift rate is increasing. There you go. All the points plotted out nice and pretty. All right. Next thing I want to show you guys is a computation table. I'm not going to do this out because this would take a little bit too long. I don't want to make this video any longer than it has to be. Okay. Let me just show you guys. This is our computation table, right? So we have our X's, we have our Y's, right? We're getting that directly from the data set right here. So all we did was we copied down all the X's into a column, and then we copied all the Y's into a column right after, right? So these are all the X's, these are all the Y's. Remember that they are data pairs, so try to line them up. Okay. Anyway, the sum of X is found by just adding up all the numbers in this column. The sum of Y is found by just adding up all of the numbers in the Y column. Then we have our X squares where you're going to square each individual number, right? So for example, the first one right here, this is actually 70 squared, which gives me 4,900. So on and so forth. You do 115, 105, etc. You're going to come out with a column like this. At the very end, you want to add all those numbers up, and that's where we get the 67,892. We're going to do the same thing with the y's, right? We're just going to square whatever we got in the y column right there, right? So this first one is just 3 squared, which gives me 9. So on and so forth, right? And then at the end, you're going to add up all of those values together. Last but not least, we're going to have our column for x times y, right? So you're just going to multiply the x values together and multiply the y values together, right? So for example, this first number up top is very simply just 70 times 3. So on and so forth. Next one would be 115 times 45, and that's how we got that number, etc. At the very end, you want to add up all those numbers, and then that's how you get the 18,458, right? Once you've completed this, and again, this is also how you show work. Once you've completed this, you just need the numbers at the bottom, those sums, right? And then we can take those sums and throw that into our computation formula. Bear with me 1 second. There we go. All right. So let's say that I was actually trying to compute R, right? You want to compute R, use the computation formula, right? First, we need to compute the sum of X, the sum of X squared, the sum of Y, the sum of Y squared, and the sum of X times Y. It is convenient to organize the data to the table, as you can see, and the sums of each entries in each column. Of course, many calculators give you these sums directly. Yes, if you're wondering, can the calculator do this for you? It absolutely can. All right. You guys can ask me about that tomorrow, right? When we do our catch-up day, if anything. Just bring in your individual calculators. The instructions of how to do this in your calculator are different for each calculator. Okay. So that's why I'm saying we'll just go over that in class individually for you. Right. Preferably bring the calculator that you know that you're going to bring to the test. All right. If you know you're going to borrow one from the library, borrow one tomorrow and bring it to class, and then I'll teach you how to use it. Right. If you know that you're going to get the 36X Pro from Staples or something, right? If you don't have it already, borrow that same exact calculator. If you do have it, bring it in and we'll talk about it. All right. Anyway, computation formula for R with n is equal to 7. And how do we have 7? It's because we have 7 pairs, right? 1, 2, 3, 4, 5, 6, 7 pairs, right? All right. So here goes the formula. R is equal to n times the sum of x times y minus the sum of x times the sum of y divided by the square root of n times the sum of x squared minus the sum of x squared times the square root of n times the sum of y squared minus the sum of y squared. Yes, the calculator can do this for you, but very simply, you write out the formula, you plug in the appropriate numbers in the correct places where they belong, little calculator magic, boom, and you get 0.949. Let's talk about what that means. All right. So, what does the value of R tell you? Since R is very close to 1, that's 9.49. I mean, excuse me, that's 0.949, right? That's, if we're talking about money, that's what, 6 cents away from being a dollar, right? So since R is very close to 1, we have an indication of a strong positive linear correlation between the wind velocity and the drift rate of sand. In other words, we expect that higher wind speeds tend to mean greater drift rates because R is so close to 1. The association between the variables appear to be linear. Right. So because it is quite a task to compute R for even 7 data pairs, right? The use of columns, as in the next example, is extremely helpful. Your value of R should always be between -1 and 1 inclusively. Use a scatter diagram to get a rough idea of the value of R. If your computed value of R is outside the allowable range, or if it disagrees quite a bit with your scatter diagram, recheck the calculations. Be sure you distinguish between expressions such as the sum of x squared, right, which is when you square all the numbers first and add them up, and the sum of x squared, which is when you add up all the x values and then square it, right? Negligible rounding errors may occur, right? So again, whenever you're doing math, you don't want to round off in the middle of your problem. You want to round off at the end of your problem, right? As you all know, I'm not a fan of rounding. Just give me all the numbers straight and I'm happy. All right. Depending on how you and your calculator round, et cetera, et cetera. All right. And yeah, different calculators round differently. Like I know when I do my math on my Android, shout out to Android, right? I get many, many, many decimal places compared to if I do it on my Texas Instrument calculator, I might only get maybe 9 or 10 decimal places, right? And as for Siri, I don't know. Not really an Apple product person, but you could try it out and tell me what you get. We'll make a comment about it in class tomorrow. Okay, anyway, what does the correlation coefficient R tell us? The correlation coefficient R is a sample statistic from a data set of ordered pairs XY. It is a measurement indicating the strength of a linear relationship between X and Y. R is a unitless measurement ranging from -1 to 1. Any R value close to 1 indicates that a positive linear relationship exists between X and Y. This means that as X increases, Y increases in the linear fashion. And R value close to -1 indicates that a negative linear relationship exists between X and Y. This means that as X increases, Y decreases in a linear fashion. Any R value close to zero indicates that the relationship, if any, between X and Y is not linear. Okay. All right. I do want to make a caution about the correlation. So, the correlation coefficient can be thought of as a measure of how well a linear model fits the data points on a scattered diagram. The closer R is to +1 or -1, the better aligned fits the data. Values of R close to zero indicate a poor fit to any line. Usually, a scatter diagram does not contain all possible data points that could be gathered. Most scatter diagrams represent only a random sample of data points taken from a very large population of all possible pairs. Because R is computed on the basis of a random sample, X and Y pairs, we expect the values of R to vary from one sample to the next, much as the sample mean X bar varies from sample to sample. This brings up the question of the significance of R. Or put another way, what are the chances that our random sample of data pairs indicate a high correlation when in fact the population's X and Y values are not so strongly correlated, right? Now, let's say the significance of R is a separate issue that will be treated in another section, right? Where we will test the population coefficient rho, which is the Greek letter pronounced rho. All right. So yeah, just to highlight that real quick, kind of taking it back to our roots, right? Jumping back to chapter 3 a little bit. All right. Just a little quick recap and bringing it forward as well at the same time, right? So R is our sample correlation coefficient computed from a random sample of XY data pairs. Rho is our population correlation coefficient computed from all the population data pairs, X and Y. So there is a less formal way to address the significance of R using a table of critical values or cutoff values. So based on the R distribution and the number of data pairs, right? This next problem at the end of the section discusses this method. The value of the sample correlation coefficient R and the strength of the linear relationship between the variables is computed based on the sample data. The situation may change for measurements larger than or smaller than the data values included in the sample. For instance, for infants, there may be a high positive correlation between their age in months and weight. However, that correlation might not apply when we extrapolate the results to people ages 20 to 30 years old, right? So the correlation coefficient is a mathematical tool for measuring the strength of a linear relationship between two variables. As such, it makes no implication about cause or effect. The fact that two variables tend to increase or decrease together does not mean that a change in one is causing a change in the other. A strong correlation between X and Y is sometimes due to other either known or unknown variables. Such variables are called lurking variables. Okay, so let's talk about this for a second, right? When you have a newborn baby, let's say like an infant, right? You would expect that as they get older, I'm talking about in months, I'm not talking about in years, right? That their weight should increase, right? So the older they are, the heavier they would be as they're growing, right? But if you had a scatter diagram to represent this information, right? One idea that we can do is we could say, okay, that line, right? That, one second, just bear with me one second. That line of best fit, it just keeps going, right? So in theory, if I was to do one of these, right, over here is a couple of months, THS, right? But when I pull it out over here, now I'm in the years category, right? So you only really looked when you were doing the work at this part here. But now when we go out to the years, you might make an educated guess to say, well, if this is true, then the older you are, the more heavier you should be, right? But you guys know from real life experience that's not true, right? So at some point we do like taper off, and then it just becomes, like we have like our usual weight, right, throughout the rest of our life, of course it's going to vary a little bit, but it's going to be kind of baseline after a certain point. This is what they're talking about. Okay. And also, correlation does not imply causation. All right, that's another thing. All right. So in ordered pairs, X and Y, right, is called an explanatory variable, and Y is called the response variable. So when R indicates a linear correlation between X and Y, changes in values of Y tend to respond to changes in values of X according to a linear model. A lurking variable is a variable that is neither an explanatory nor a response variable, yet a lurking variable may be responsible for changes in both the x and the y. All right, let's look at an example of this. All right. This is really, really interesting right here. Really, really interesting. All right. Let me get y'all a real nice example that'll make this clear for you. Okay. Whoops. Didn't hit the right button there a second ago. All right, so now we're going to talk about causation and lurking variables, right? So, over a period of years, the population of a certain town increased in size. It was observed that during this period, the correlation between X, the number of people attending church, and Y, the number of people in the city jail, was R is equal to 0.9. So, there is a strong positive correlation that as more people attend church, more people go to jail. Does going to church cause people to go to jail? Is there a lurking variable that might cause both variables x and y to increase? All right. So here we go. We hope church attendance does not cause people to go to jail. During this period, there was an increase in the population of the area, right? Therefore, it is not too surprising that both the number of people attending church and the number of people in jail increased, right? Because the population overall increased. So a high correlation between X and Y is likely due to the lurking variable of population increase. Okay. The correlation between two variables consisting of averages is usually higher than the correlation between two variables representing corresponding raw data. One reason is that the use of averages reduces the variation that exists between individual measurements, right? i.e., the central limit theorem. A high correlation based on two variables consisting of averages does not necessarily imply a high correlation between two variables consisting of individual measurements, right? As you're about to see. Doo, 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 doo. All right. And that's it for that. So that's our scatter diagrams, right? And our linear correlation. So on your test, what's going to happen? I'm going to give you a set of data. I'm going to ask you to draw for me, right? A scatter diagram, right? With the dots and all of that, right? Then I'm going to ask you a second question. Would you estimate that the correlation coefficient R is positive or negative? Right? It's also going to ask you for zero as well, but as I told you, the zero is a trick. It's either positive or negative based on the information that you have. All right. Last but not least, I'm going to ask you to interpret your results. And again, if you have a positive correlation as X is increasing, Y is increasing. If you have a negative correlation as as X is increasing, Y is decreasing. Okay. You can look back in the video to see that. All right. And then I want to start off with a very, very, very difficult topic. A very, very difficult topic. This whole class, we've been talking about statistics, some arithmetic and algebra here and there, but we've just been talking about statistics. But the class is not called statistics alone, right? This is called probability and statistics. So, the heck is probability? What is that? Right? Let's talk about it a little bit. Let's talk about it. All right. This is going to be our first introduction to what is probability. All right. This is going to be some interesting and really, really cool stuff. Promise you that. All right. And then we're gonna you could think of this as like the second, yeah, like the second third of the course, right? And then at the end, we're gonna put it all together. We're gonna put probability and statistics together. All right. But we're gonna talk about that right now. All right. We're gonna talk about what it is and how it's gonna come together in the end. But anyway, right? We encounter statements in terms of probability all the time. An excited sports announcer claims that Sheila has a 90% chance of breaking the world record in the upcoming 100-meter dash or yard dash, whatever, right? Henry figures that if he guesses on a true false question, the probability of getting it right is one half. That's true. The Right to Health lobby claims that probability is zero point 0.4 of getting an erroneous report from a medical laboratory at a low cost health center. It is consequently lobbying for a federal agency to license and monitor all medical laboratories. When we use probability in a statement, we're using a number between 0 and 1 to indicate the likelihood of an event. Okay? So probability is a numerical measurement between 0 and 1 that describes the likelihood that an event will occur. Probabilities closer to 1 indicate that the event is more likely to occur. Probabilities closer to 0 indicate that the event is less likely to occur. Okay? When you look at your formula sheet, you're going to see things like this. P open parentheses, A close parentheses, which is read as the probability of A, P of A, or the probability of event A. If the probability of A is equal to 1, the event is certain to occur. If the probability of A is equal to 0, the event A is certain not to occur. Okay? Now, it is important to know what probability statements mean and how to determine probabilities of events, because probability is the language of inferential statistics. All right. Now, that word right there, inferential statistics, that's what all of this is all about, right? I don't necessarily care about what you or one of your classmates thinks about the overall let's say status of the government, for example. Like, do we feel like Donald Trump is doing a good job or not, right? We individually don't doesn't really like tell me what the country feels, right? I want to know in general, what does the country feel, right? But for many reasons, could be too expensive, could be impossible. For many reasons, I can't gather the information on the country, right? What I can do is I can take a sample, right? Like our class, ask everybody, what do you think? What do you think? What do you think? And from that information, I could make an educated guess. I can make an inference, right? Inferential statistics. I can make an inference as to what the population parameter would be, right? That's the whole point of all of this. All right. So let's take it back a step though. Let's take it back a step. Let's talk about probability. Right. We're gonna get to inferential statistics in a little bit later. All right. Probably next month. But it's gonna be it's gonna be good. It's gonna be good. All right. So let's talk about probability assignments, right? A probability assignment based on intuition incorporates past experience, judgment, or opinions to estimate the likelihood of an event. A probability assignment based on relative frequency uses a formula, right? The probability of an event is equal to the relative frequency, which is the number of occurrences divided by the total number of everything, right? So F is the frequency of the event occurring, and N is the number of observations. All right. Three, a probability assignment based on equally likely outcomes uses the formula probability of event is equal to the number of outcomes favorable to the event divided by the total number of outcomes. All right. And these are the three ways that we understand and figure out probability. All right. Let's look at some examples real quick. All right, probability assignment. So consider each of the following events and determine how the probability is assigned. Let's say a sports announcer claims that Sheila has a 90% chance of breaking the world record in a 100-meter dash, right? It is likely that the sports announcer used intuition based on Sheila's past performance, right? So basically, I seen Sheila run the 100-yard dash, right? And I feel like in this next upcoming meet, this is going to be the one she could break the record, right? I'm using my intuition, all right? Henry figures that if he guesses on a true or false question, the probability of getting it right is 0.5, right? All right, so let's talk about this. So in this case, there are two possible outcomes. Henry's answer is either correct or incorrect. Since Henry is guessing, we assume the outcomes are equally likely. So there are two equally likely outcomes and only one is correct, right? Very simple, right? You have true or false question test. One answer is correct. You have a one out of two chance of getting the correct answer. As simple as that, right? So the probability of a correct answer is the number of favorable outcomes, the correct answer divided by the total choices that you have, which is 2, 0.5. How about this one now? All right. A little bit more specific. The right to health lobby claims that the probability of getting an erroneous medical laboratory report is 0.40, based on a random sample of 200 laboratory reports, of which 80 were erroneous, right? So now the formula for relative frequency gives the probability with sample size n is equal to 200 and number of errors f is equal to 80, right? So the probability of an error is going to be equal to our relative frequency, which is the number of errors, the total number of errors, 80, divided by, right, the total number of everything, 200. And that's how we get the 0.40, right? So you see how this one's using more detailed facts, right? But make you guys' lives easy, right? This is all the same thing, right? Number of successes, number of favorable outcomes, whatever, divided by the total number of everything. Just remember that probability is it can only be between 0 and 1. It can be a fraction, it could be a percentage, whatever, right? It can only be between 0 and 1, right? So that being said, you always take your number of successes divided by the total of everything. And that's what does it all for you. You know? Very simple. All right. So next we want to talk about expressing our probability results. All right. Okay, so the probability of an event A is the number between 0 and 1. There are several ways to write the numerical value of the probability A as a reduced fraction in decimal form, rounding to 2 or 3 digits after the decimal is appropriate for most applications, as a percent, or as an unreduced fraction. This representation displays the number of distinct outcomes of the sample space in the denominator and the number of distinct outcomes favorable to event A in the numerator. Needless to say, which one do I like? I like D the best, right? I do not like reduced fractions. I don't like the decimals, none of that, right? Give me that unreduced fraction, right? I want to know the number of successes in your experiment divided by the total number of everything. When you're doing your homework, when you're on the test, you're gonna give me an answer for probability. Just do this for me, right? The number of successes divided by the total number of everything. That's it. Don't worry about typing in the calculator and reducing it and give me that, none of that, right? Just give me this right here, right? I'm not interested in the 0.40. I love the 80 over 200. That's what I want, right? So we've seen three ways to assign probabilities: intuition, relative frequency, and when outcomes are equally likely, a formula. Which do we use? So most of the time, it depends on the information that is at hand or that can be feasibly obtained. Our choice of methods also depends on the particular problem, right? So in the guided exercise, you will see three different situations and you will decide the best way to assign the probabilities. Remember, probabilities are numbers between 0 and 1. So don't assign probabilities outside of this range. You guys are gonna have some test questions, excuse me. You're gonna have some homework questions on that. Okay. The technique of using the relative frequency of an event as the probability of that event is a common way of assigning probabilities and will be used a great deal in later chapters. The underlying assumption we make is that if events occurred in a certain percentage of times in the past, they will occur about the same percentage of times in the future. In fact, this assumption can be strengthened to the very general statement called the law of large numbers. All right. So bear with me 1 second. Okay. So the law of large numbers, right? So in the long run, as the sample size increases and increases, the relative frequencies of outcomes get closer and closer to the theoretical actual probability value, right? So that's the law of large numbers right there. More samples I take, the closer and closer I get to what the actual um probability or number would be. All right. So the law of large numbers is the reason businesses such as health insurance, automobile insurance, and gambling casinos can exist and make a profit. No matter how we compute probabilities, it is useful to know what outcomes are possible in a given setting. For instance, if you're going to decide the probability that hand scrabble, right, will win the Kentucky Derby, you need to know which other horses will be running. To determine the possible outcomes for a given setting, we need to define a statistical experiment. So let's recap a little bit. A statistical experiment or statistical observation can be thought of as any random activity that results in a definite outcome. An event is a collection of one or more outcomes of a statistical experiment or observation. A simple event is one particular outcome of a statistical experiment. The set of all simple events constitutes the sample space of an experiment. All right. Good stuff, good stuff. Let's look at an example real quick. Let's look at an example real quick. We're gonna throw it back for a second. We're gonna do a really fun activity. It's an oldie but a lovely. All right. We're gonna talk about genotypes. All right. Little biology example right here. So using a sample space. So human eye color is controlled by a single pair of genes, one from the father and one from the mother. This is called a genotype. Brown eye color, represented by capital B, is dominant over blue eye color, which we're going to represent by lowercase l. Therefore, the genotype, capital B, lowercase l, consisting of one brown gene, right, capital B, and one blue gene, lowercase l, the brown gene dominates. A person with a a brown dominant blue I forgot what the word is, right? I want to say subdominant, but recessive. I think that's the word. Recessive genotype has brown eyes. If both parents have brown eyes and have genotype, right? Brown dominant, blue recessive, what is the probability that their child will have blue eyes? And what is the probability that a child will have brown eyes? Okay, let's look at this real quick. Let's look at this real quick. All right. Awesome, awesome, awesome. One second. Do. Nickelodeon. All right. One second. Coming back now. All right. So to answer these questions, we need to look at the sample space of all possible eye color genotypes for the child. So here we go, right? You have the father. This is his dominant brown eye gene, and this is his recessitative blue eye color gene. Excuse me. For the mother, we have the same thing, dominant brown, blue recessive, right? And when they come together, this baby right here is a dominant brown eye baby, right? Brown and brown, right? This baby here, right, will have the recessive blue gene, right, with the dominant brown gene. This baby will have brown eyes, but this baby will have the ability to have children with blue eyes. This baby is the same story over here, right? This baby has the brown dominant eye color as well as the recessive blue eye color. But this baby, when you look at them, will have brown eyes, but will have the ability to have babies in the future with blue eyes. And this baby right here, this baby will have the blue eye gene and stuff. Like you will see the blue eyes in this baby, and they can make a baby with blue eyes. Okay, anyway, according to genetics theory, the four possible genotypes for the child are equally likely. Therefore, we can use the formula to compute probabilities. Blue eyes can occur only with the recessive genes blue genotype. So, there is only one outcome favorable to blue eyes, right? So, it's 1 out of 4, right? That's the probability of the baby having blue eyes, right? So the probability of blue eyes is equal to the number of favorable outcomes, which is 1, out of the total number of outcomes, which is 4. Brown eyes occur with the 3 remaining genotypes, right? Brown blue, and blue brown. By the formula, the probability of brown eyes is the number of favorable outcomes, which is 3 out of 4. Okay, this is good stuff. Good stuff. Okay. So there is another important point about probability assignments of simple events. The sum of the probabilities of all simple events in a sample space must equal 1, right? Very simply put, the sum of all the probabilities in the sample, whatever you're looking at, must add up to 1. Okay? By the way, if you're wondering where we're at right now, using your formula sheet, we're on the probability section. This is going to be in chapter 5, all right, which is the upper right-hand corner, right? Upper right-hand corner of your formula sheet. Right? Okay. So we can use this fact to determine the probability that an event will not occur. All right. For instance, if you think the probability is 0.65 that you will win a tennis match, you assume that the probability is 0.35 that your opponent will win. The complement of an event A is the event that A does not occur. So we use the notation A complement to designate the complement of event A, right? This next figure is going to show right? The events A and its complement event A and its complement A complement, right? In the literature, the symbols A prime and A bar are also used to designate the complement of event A, right? Notice that the two distinct events A and A complement make up the entire sample space. Therefore, the sum of their probabilities is 1. Okay? So here we go. The complement of event A is the event that A does not occur. A complement designates the complement of event A. Furthermore, the probability of A plus the probability of A complement is equal to 1. The probability that event A does not occur is equal to the probability of A complement, which is equal to 1 minus probability of A. This is in your formula sheet. You don't need to remember it, right? But I believe that everybody here can kind of understand this to some degree. If I'm watching the news and the weather forecast person tells me, "Hey, there's a 70% chance it's going to rain tomorrow." That's what they're telling me. They're telling me there's a 70% chance it's going to rain tomorrow. What's the complement of it raining tomorrow? That means that there's a 30% chance that it will not rain tomorrow, right? 70% chance that it will rain, 30% chance it will not rain tomorrow. All right. That's the idea of a complement. Okay. Let's look at another example. All right. Complement of an event. The probability that a college student who has not received the flu shot will get the flu is 0.45. What is the probability that a student will not get the flu if the student has not had the flu shot? So in this case, right, we have the probability of will get the flu is equal to 0.45, and the probability of will not get the flu will be 1 minus the probability of you getting the flu, which is 1 minus 0.45, which is equal to 0.55. Very simple, very simple, very simple. All right. Just to make me feel good, I'd like to show you guys a Venn diagram that to me explains everything, right? So when you look at this diagram right here, right? So the blue part here, that's the probability of event A, whatever that is, right? Everything that's on the outside of the blue circle, right? That's the complement. That's A complement. The probability that A will not occur, right? If you put them together in the same picture, right, that makes up your total sample space, right? And that will be equal to 100% or to 1. Okay. All right, just want to do a quick summary of probability real quick, just some cold hard facts real quick. All right. So a statistical experiment or statistical observation is any random activity that results in a definite outcome. A simple, right, event consists of one and only one outcome of the experiment. A sample space is a set of all simple events. An event A is a subset of the sample space. The probability of event A is denoted by probability of A. The probability of an event is a number between 0 and 1. The closer to 1 the probability is, the more likely the event will occur. The closer to 0 the probability is, the less likely that it is to occur. All right. The sum of the probabilities of all simple events in a sample space is one. So when you add up all the probabilities together, they have to add up to one. And if what happens if they don't add up to one, right? Then that's not a valid probability, that's not a valid sample space. Probabilities can be assigned by using intuition, relative frequency, or the formula for equally likely outcomes. Additional ways to assign probabilities will be introduced later. The complement of event A is denoted by A complement. So A complement is the event that A does not occur. And also the sum of the probability of A plus this plus the probability of A complement is equal to one, right? As per the Venn diagram that you guys just saw. All right. And then almost done, almost done. We're just wrapping it up right now, wrapping it up right now. Okay. We're almost there. So, as stressed in item three in the summary about probabilities, the closer the probability is to one, the more likely the event is to occur. The closer the probability is to zero, the less likely the event is to occur. However, just because the probability of an event is very high, it is not a certainty that the event will occur. Likewise, even though the probability of an event is very low, the event might still occur, right? Events with low probabilities but big consequences are of special concern. Such events are sometimes referred to as black swan events. So, as discussed in a very popular book, The Black Swan by Nassim Nicholas Taleb, right? In his varied careers, Taleb had been a stock trader, author, and professor at the University of Massachusetts. His special interests are mathematical problems of luck, uncertainty, probability, and general knowledge. So, in his book, The Black Swan, Talib discusses the impact of the highly improbable. So, if an event has little impact, bearing, or meaning on a person's life and a very low probability, then it seems reasonable to ignore the event. All right. Okay. Almost there. Almost there, you guys. However, whoops. However, some really big mistakes in a person's life can result from misjudging either the size of an event's impact or the likelihood the event will occur. An event of great importance cannot be ignored, even if it has a low probability of occurrence. So, what should a person do? Talib describes himself as a hyper skeptic when others are gullible, right? And gullible when others are skeptical. In particular, he recommends being skeptical about mentally confirming an event when the errors of confirmation are costly. Lots and lots of data should be thought of as confirming an event when a simple instance can disconfirm an important and costly event. Talib recommends that one be skeptical in the face of wild randomness and big consequences, and gullible when the randomness and consequences are mild. One way to estimate the randomness of a situation is to estimate its probability. So, estimating the consequences of an event in your own life must be a personal decision, right? So, real quick, what does probability of an event tell us? The probability of an event A tells us the likelihood that event A will occur. If the probability is one, the event A is certain to occur. If the probability is zero, the event A will not occur. Probabilities closer to one indicate the event A is more likely to occur, but it might not. Probability closer to zero indicate that an event A is likely to is less likely to occur, but it still might. Right? Okay, okay. What's a good example I could give you guys? All right. I follow basketball. I'm not sure if everybody else does, but currently, right now, um, the Knicks make me mad, right? So using my intuition, right? Whenever a lesser team, right, plays the Knicks, and what qualifies a team to be a lesser team in my opinion, right? I look at the rankings that each team is in for like the Eastern Conference or for the Western Conference. When a lesser team plays the Knicks, I'm expecting, mind you, the Knicks are ranked third in the Eastern Conference right now, or at least the last time I checked, right? When a lesser team that's ranked 14 or 10 or whatever comes to play the Knicks, I'm expecting the Knicks to destroy them, right? If I had to take a bet, I would say the probability of the Knicks winning is high, right? And then here comes the Knicks and they lose. Shaking my head. Then, when you have a better team, right? A team that's ranked like one or two in their conference, right? Like the Spurs, for example, come and play the Knicks, and the Knicks destroys them, and they're arguably one of the best teams in the league right now. I think they have only 15 games that they've lost out of like 50 or something, right? But they can't beat the Knicks. I can't explain it. Can't explain it, right? But we can use probability to estimate these things from happening, right? Those of you old enough to make bets, you guys could go on FanDuel and all that and increase your money if you want to, right? Not telling you to do that though. Right? All right. So the probability of event A applies only in the context of conditions surrounding the sample space containing event A. For example, consider the event A that a freshman student graduates with a bachelor's degree in 4 years or less. Do events in the sample space apply to entering freshmen in all colleges and universities in the United States or just a particular college? Are majors specified? Are minimal SAT and ACT scores specified? All these conditions of events in a sample space can affect the probability of an event. It would be inappropriate to apply the probability of event A to students outside these described in the sample space. All right. Almost there, almost there. All right. So if we know the probability of event A, then we can easily compute the probability of event not A in the context of the same sample space. The probability of not A is equal to 1 minus the probability of A. So, probability related to statistics. We conclude this section with a few comments on the nature of statistics versus probability. Although statistics and probability are closely related fields of mathematics, they are nevertheless separate fields. It can be said that probability is the medium through which statistical work is done. In fact, if it were not for probability theory, inferential statistics would not be possible. It would be so sad. Put very briefly, probability is the field of study that makes statements about what will occur when samples are drawn from a known population. Statistics is the field of study that describes how samples are to be obtained and how inferences are to be made about unknown populations. A simple but effective illustration of the difference between these two subjects can be made by considering how we treat the following examples, excuse me. So example of probability application condition. We know the exact makeup of the entire population. For example, say we have three green marbles, five red marbles, and four white marbles in a bag, and you draw six marbles at random out the bag. What is the probability that none of the marbles is red? Right? So we know all of the whole population in that example, right? Give you guys another example. All right. Here's another one. So in this condition, right, we have only samples from an otherwise unknown population. So if we draw a random sample of six marbles from an unknown population of all marbles in the bag and observe their colors, based on the sample results, we can make a conjecture about the colors and numbers of marbles in the entire population of all marbles in the bag. All right. So I don't like, let's say there's an infinitely large bag. I don't know all the marbles in that bag, but I took six out of the bag and based off of the colors of the six marbles that I chose, I can make a guess, a guesstimate, an educated guess, right? I can make an inference about what the entire bag is holding, right? Right. In another sense, right? Probability and statistics are like flip sides of the same coin. On the probability side, you know the overall description of the population. The central problem is to compute the likelihood that a specific outcome will happen. On the statistics side, you know only the results of a sample drawn from the population. The central problem is to describe the sample, descriptive statistics, and to draw conclusions about the population based on sample results, which is inferential statistics. In statistical work, the inferences we draw about an unknown population are not claimed to be absolutely correct. Since the population remains unknown in a theoretical sense, we must accept a best guess for our conclusions and act using the most probable answer rather than the absolute certainty. So, probability is a topic of this chapter. However, we will not study probability just for its own sake. Probability is a wonderful field of mathematics, but we will study mainly the ideas from probability that are needed for proper understanding of statistics. All right. And that's it for today. All right. I hope you all have a blessed and happy night, happy day, and I'll see you all tomorrow. All right.